Okay. So greetings. So let's get started with this session. So if you recall in the previous session, we were looking at this controller block, right? After having looked at the overall uh, closed loop system block diagram. So let's continue from here, right? So and then we will see how we can proceed forward. In fact, one of the most common controllers, that are used, in the domain, or what are called as the PID, okay, proportional integral derivative control. So what is this PID controller? Professional integral derivative controller. You know, we will learn about them, and then we will learn about each term one by one, right? So first, let's look at this proportional term. What is called as a proportional control. So what is this proportional controller? So in a proportional controller, what we do is the following. So we take in the error signal, okay, E of t, and then we just multiply it by a constant Kp, okay, which is called as a proportional gain, and then we get the control input U of t. All right, so that's it. It's a very simple block wherein the controller block is only a constant scalar. Okay, so consequently, the reason it's called as a proportional controller is that because the control input U of t is directly proportional to U of t. Okay, so that's why it is called as a proportional controller. So consequently, if you
control output rates.
I'm sorry, what is it? The control input is the so okay, there is a subtle difference. U of t is the output from the controller block, but then its name is called as control input because U of t is the input to the system, right? And when the controller calculates the input, it's called control input. Okay. So I think good observation. So let me clarify. As a friend pointed out, should it be control output? It is the controller output. Okay, but it's a control input. I hope the subtle difference in terminology is clear. Okay, so U of t is the input to the system or the plant, which is calculated by the controller. So consequently, it is what is called as the control input. Okay, so I hope the difference is clear, right? Yeah. Okay. So now, if you take the transfer function, if you take the Laplace transform on both sides, I think what will we get if we take the Laplace transform on both sides? What will be the relationship between E of s and U of s? So because you can immediately write that U of t is going to be Kp times E of t, right? So if you take the Laplace transform, what will happen?
U of s equal to Kp times E of s.
So U of s, if we take Laplace transform on both sides, U of s will be only Kp times E of s. This implies that what will be the corresponding controller transfer function?
U of s divided by E of s.
So it's going to be U of s by E of s. That's what it is going to be. In this case, what will happen? It will be just Kp. Right? Yeah. So what to say? That's what we will have. Okay. So if we have what to say, this proportional controller, we have Kp to be the plant transfer function. Okay. So essentially, we get the plant transfer function to be Kp, and this Kp, due to this reason, this is the way it is used. is also what is called as a proportional gain. So what is this proportional gain? It is the parameter that comes in the controller transfer function. So as I told in the previous session, so if we look at how the controllers are designed, by and large we fix the structure. Is essentially the what to say? We want to design the controller such that we fix the values of certain parameters that come in the controller function. So consequently, when we look at the controller, proportional controller, the only parameter which plays a role is this Kp, and Kp is a real number. Okay, so it is a real scalar. And that's what is called as a proportional gain. All right. So this is a very simple controller. So if you look at the pros and cons of this proportional controller, if you look at the advantages, so it is very simple in structure, easy to implement. Okay, so that way it is very handy. All right, as far as practical design is concerned. But what are the limitations? If you look at the cons, okay, what happens is that like we will look at such cases. What are these cases? But in some cases, in some instances, proportional control can lead to a non-zero steady state error. Okay, so proportional controller can lead to non-zero steady state error. Steady state error while tracking or while following even like constant inputs. Constant reference. Oops, sorry. While tracking constant reference inputs. Okay, we look at such cases. Okay, as we go along. So this is a limitation. Not always, but some cases. Okay, so but in summary, a proportional controller is a very simple, straightforward controller. Okay, so it is the first controller that one could try out. Like it's a one parameter controller in the sense that why are we calling it as one parameter? Because there is only one parameter Kp, which is the proportional gain that one needs to look at. All right, so that's it. Okay, it's a simple structure. Okay, and it's easy to implement. All right. So now let's look at the second block. Okay, in PID. So the second block is integral controller. Okay, I stands for integral. So what is this integral controller? Like if you look at the integral controller, as the name indicates, the structure of the integral controller is such that the control input u of t is going to be some constant multiplying the integral of the error. Okay. So what we do is that like we take the integral of the error, okay, in a time interval, we integrate that error history, and then we multiply with a parameter called ki, which is called as the integral gain, okay, and the ki being some real number, and then like that will be the control input. Okay, so if we want to look at it graphically, what will happen is that the following, right? So let's say we draw the time history of this one, okay, of the error. So if we draw some arbitrary profile, right? So what is this integral controller going to do? Like let's say if I am at some specific time t, we are going to integrate. Okay, so graphically integration will give me the area under the curve, right? Is it not? So I'm going to get this area, which will then one can evaluate, right? So to figure out what will be the error, right? So that one needs to work with. Okay, so that is the notion of an integral controller. Okay, So if we take the Laplace transform on both sides, what are we going to get? We will immediately get U of s is going to be equal to Ki multiplied by E of s divided by s, right? So if you use a property of the Laplace transform, all right, which is the Laplace transform of definite integrals, right? So we divide by s. So this implies that the controller transfer function, which is U of s by E of s, okay, now comes to be Ki by s. Okay, so we can immediately observe that in the case of an integral controller, the transfer function of the integral controller block is K by S. Okay, fine. So one important thing, like that we can immediately we have to note, okay, which we will also discuss later on, is one challenge for us when we design integral controller is that it introduces an open loop pole at 0. Okay, we can immediately observe that, right? Because its structure is Ki by S, right? So if you look at the open loop transfer function, it is G of S times H of S, and G of S contains C of S, right? So obviously there is going to be a 1 by S term, right? Of course, Ki by S to be very specific, but then like you can see that there is going to be a S term in the denominator of the transfer function, right? The open loop transfer function. So it introduces an open loop pole at 0. Okay, so that's something which we need to be aware of, right? Okay. So in fact, if you look at this, one main advantage of integral controller is that it considers the history of error, right? So we can observe that when we are calculating the integral of the signal E of t, we are taking into account the historical evolution of E of t, right, in the design of the controller, right? So that's also something which is pretty useful, okay, as we go. Okay, so that's something which we need to keep in mind, all right? So when we are designing an integral controller. Okay, once again, what are the forms of this integral controller? So the main advantage is that this integral controller can help us, okay, in avoiding or eliminating zero or eliminating steady state error, okay, or ensuring zero steady state error, at least theoretically, for tracking constant reference. Okay, so essentially, it leads the use of an integral controller leads to zero steady state error, at least in theory, right? Zero steady state error in tracking, while tracking constant reference. Okay, so that's what we should remember about the integral controller. Okay, but what is the con, right? Well, of course, there are going to be limitations, right? So one thing with integral control is that, like, please note that, right, as time progresses. That means that as we keep on moving forward in time, what's going to happen is that the errors are going to keep on accumulating, right? Are they not? Like even if we consider the curve that we have looked at, right? So we can immediately observe that, we have this integral controller wherein the error is keep integrated. All right. So if that is the case, what may happen is that we can have a scenario where potentially, the integral of the error may go to such an extent that it may exceed the capability of the actuator. See, please note that, we need to realize the control input using an actuator, is it not? Okay. If we if we demand a lot of control input by integrating past errors, and if the number that we are calculating integral controller or as a to have a problem, right? Is it not? Because we will essentially go outside this capability of the uh, actuator, then we may have a problem, right? So that's what is the flip side. Okay. So the con is then the use of an integral controller, can lead to actuator saturation. So what is called as actuator saturation? Suppose, let us say we have a force actuator, right? And whose capability is 100 newtons of force, just as an example. And we demand, let's say 105 newtons from it, okay? The integral controller calculates and it demands 105 newtons. There is no way that actuator can satisfy that, right? So consequently, we are going to have what is called as actuator saturation, right? So the expectation from the integral controller may exceed the. Hello, any questions? Okay, so that is the integral controller. Then on, we go to what is called third block, okay, in the PID controller. Okay, so PID once again stands for proportional integral derivative control. Okay, so what is this derivative controller? As the name suggests, in this case, the control input is going to depend on the derivative of the error signal, right? So the derivative of the error signal is going to be dE dt, right? And we are essentially going to multiply it by a scalar kd. So kd is what is called as the derivative gain. Okay, once again, a real number, okay, a real scalar. So essentially, we are going to have this to be the derivative gain. All right. Okay. So in fact, now if you take the Laplace transform on both sides, of course, for the time being, we neglect the initial condition. The initial error need not be 0, but then like we are only looking at the transfer function. So we substitute the initial condition to be 0. So consequently, the controller transfer function u of s divided by e of s becomes kd. Okay, so this is the controller transfer function in this particular case. That is the derivative. Okay, so we can immediately see that the derivative controller introduces an open loop 0 at 0. Okay, so we can observe that we have an open loop 0 at the origin. Okay, so as per some perspective of the derivative controller is concerned, right? Yeah. So now, if we look at the derivative controller per se, right? And we look at the pros and cons, okay, of this derivative controller. What will happen? Okay, so what does this derivative controller do? Like, let me take a similar, let's say, time history plot of E of t. So let's say we plot E of t and time. Okay, and let us say, this is our time history once again, and we are at some time t. Okay, so all of us know that, like the derivative gives us the slope at the time, right? So in essence, what is happening is that we are going to have some sort of anticipation from a derivative controller, isn't it? So because if you look at it, like mathematically, we are taking the derivative, and from a what to say, from a geometric perspective, we are getting the slope of the curve, right, at time t. So consequently, what's going to happen is that like we are going to have some information about what could potentially what to say come, like from the controller or come from the signal time history in the immediate future. Okay, so the derivative controller gives us some anticipatory behavior, right? So it gives us some yeah, on it being in anticipatory nature. Okay, so we get some anticipatory feel, like to the controller design per se, right? So that's one advantage of a derivative controller. Okay, but there are some cons associated with the derivative controller too. Next, see what are some potential limitations associated with derivative controllers. See, for example, let us say we have a constant error signal. Okay, if you have a constant error signal, like we take the derivative, we essentially are going to get zero. So the derivative controller will not be able to correct for constant non-zero error signal. Okay, that's one thing, right? But more importantly, like let's consider an important limitation is the following. Let's say we take the case wherein we have an error signal like this. I'm just constructing a case just so that I can convey the point to you. Let us say we have an error time history, like this is like this. Okay, so let us say it is like a sinusoidal signal. It's a low frequency sinusoidal signal, that's the error. But then like there is some high frequency, low amplitude noise on top of it. Okay, so we are having a low frequency error signal. On top of it, we are going to have high frequency, low amplitude noise. So as an example, let's say we take the error signal to be some sine t. Okay, then we have, let's say, some 10 power minus 2 sine 100. Okay, so I'm just taking an arbitrary example. Okay, so just to show the point. So this 10 power minus 3 sine 100t is, as we can see, low magnitude. The magnitude is 10 power minus 2. It's 2 orders of magnitude lower than the main signal, but high frequency. Okay, it's a low magnitude, high frequency. Alright, so now what happens if we take the derivative of the signal? We can immediately observe what's going to happen, right? So if I take the derivative of the signal, we essentially can understand one of the limitations, right? So if you take the derivative, we'll get cos t, which should have been ideally the derivative, and then we get cos 100t, okay? Because we are going to get 10 power minus 2 times cos 100t times 100, right? So we are going to get cos 100t, okay? So this is an issue, all right? Because what is happening? The signal has now been modified in such a way that the low amplitude, high frequency noise completely masks what should have been the ideal derivative. See, ideally the derivative should have been cos t, right? Which is this form. But then what happens is that like this high frequency noise will completely mask it. Okay, cos 100t will essentially oscillate between -1 and +1 and very high frequencies, right? It will completely mask it. So there is an issue, right? So the derivative controller amplifies high frequency, okay, which is a problem. Okay, although to begin with the noise might have been low frequency, right? Sorry, it's low amplitude, okay, but since its frequency is high, the derivative controller amplifies the low frequency, high magnitude, high frequency. Sorry for that. Okay, so that's what happens with the derivative control. That's one limitation with derivative control, right? Like that should be kept in mind, right? When we are implementing derivative control. So, as an exercise, I want you to think through how we can circumvent it, like, so please look at tools like MATLAB, like, and any other software, like where this PID controller is implemented. Yeah, please find out how this derivative in practice, and then please get back to me in the next session, right? So as to how one can actually what to say, realize this derivative control in practice, so as to avoid this issue, okay, as far as amplification of the high frequency noise is concerned. Okay, so this is the third block. Okay, this is the derivative block. All right. So any questions? Three sort of like foundational blocks of this PID class of PID controllers. So what happens is that, like, people use different combinations. Okay, so typically a P controller is tried out. The integral and derivative controllers are rarely tried out as standalone controllers. What do I mean by that? Like, people hardly try out I controller separately or D controller separately. Okay, if a proportional controller is not working well, someone may try out a PI controller. Okay, so what is a PI controller? PI controller is a proportional integral controller where the controller transfer function is going to be equal to Kp plus Ki divided by S. Okay, so that's what will happen. So Kp plus Ki divided by S, this will result in Kps plus Ki divided by S. So that's what we will have. So this introduces an open loop 0 at minus Kp, Ki by Kp, sorry. Okay, because we can immediately see that the root of the numerator polynomial is minus Ka by Kp. It introduces an open loop 0, sorry, open loop pole at 0. So why are we saying this? Because please remember, the open loop transfer function is nothing but G of S times H of S, right? And we know that G of S is going to be C of S times P of S, right? So we can immediately observe that whatever zeros and poles are introduced in our choice of C of S automatically get added as open loop poles and open loop zeros. Okay, so I think we need to be aware of. Okay, so a pole associated with the controller transfer function becomes an open loop pole. Okay, a zero associated with the controller transfer function becomes an open loop zero, and so on. Okay, so that's something that is very important for us to remove. All right. Okay, so this being the case, so PI controller becomes a two-parameter controller. So immediately we can see that there are two parameters, P and Kp and Ki, that need to be calculated. Okay, with the PI controller. Okay, so then one can choose a PD controller. So what is a PD controller? As the name indicates, it's proportional derivative. Okay, so essentially we have the transfer function of Kp plus Kds. Okay, so you can see that as a standalone transfer function, it's an improper transfer function, right? Because the order of the numerator polynomial is 1, the order of the denominator polynomial is 0. Okay? So as a standalone transfer function, this is not a proper transfer function. Okay, so and this here we have an open loop 0 introduced at minus Kp by Kp. Okay, so that's what happens with the PD controller. Once again, it's a two-parameter controller. Right? So, and the more generic one, once again, people hardly use ID. Okay, the proportion term is typically used. Okay, so we use PI, PD, or PID. Okay, so PID, as the name suggests, will include all the three blocks. Okay, Kp, Ki, yes, please.
With respect to the PD controller, if you see the order of the numerator is 1, but the denominator there is no term. Can we take it as a non-causal one?
So you can immediately see that that's a good point. Okay. In fact, I was about to come to that point after completing PhD, but since the question has been raised, let's address it now. So as a friend Angarasu pointed out, you see that in PD controller, the numerator order is 1, the denominator order is 0, right? So obviously, it becomes an improper transfer function. So shall we say the controller is non-causal? Yes. If you look at the controller as a standalone block, it becomes a non-causal entity with PD controller, right? And what is the notion of a non-causal controller? It is anticipative, right? That's what the derivative term brings up, right? So now I hope you can connect the dots, right?
Yes.
Why we said that for causal system, the numerator order should be lower than or equal to the denominator order, because you can immediately see that when the reverse is true, that is the numerator order is greater than the denominator order, we get anticipatory behavior, right? In the PD controller, the anticipatory behavior comes due to the derivative term. Okay. Yeah.
So because of the derivative, because of the presence of derivative control term, we are getting it as a non-causal. Is it perception?
Non-causal block. Let me be very clear. The controller, if you consider it as a standalone block, it becomes non-causal. You are correct. However, please note that the controller is only one component of the closed loop system. Okay, the entire closed loop system will be causal. Okay, when we design it, and the closed loop transfer function will be a proper transfer function.
Okay.
So once again, let me reiterate. This is a good point. If you look at the open loop transfer function, it is g of s times h of s. So you can see that it is a product of the controller transfer function, the forward path, the plant transfer function, and the feedback path transfer function, right? So with the PD controller, yes, the controller transfer function as a standalone entity may be not proper, but then when you consider it in combination with P of s and H of s, the open loop transfer function will become proper. Okay, that's how we'll design. Okay. Okay, so ultimately we will use PD derivative controller only in such scenarios where we can be assured that when it's used in conjunction with the plan, the open loop transfer function and the closed loop transfer function will be proper transfer function. Okay, so that's important. Okay?
Professor, one more doubt. What exactly is proper or non-proper? Because if it is a non-causal, then it is anticipative nature. Then it is good, right? Why we are calling it as a non-proper?
That is the definition of the transfer function. If you look at any transfer function, okay, it's a ratio of two polynomials in S, right? The numerator order is M, denominator order is N. So for a proper transfer function, we need M should be less than or equal to M. Okay. So please don't correlate non-proper or improper transfer function as a negative connotation. That's not the intention. Okay, that's the terminology. Okay. All right. It's just the jargon which is used.
But the thing is, if the system is anticipative, then it is good right as a system because it is predicting the future and responding for that.
Okay. So let's look at that. Okay. So the question becomes, hey, look, if I have all my systems to be non-causal, right? That is like it is anticipating, even the open loop system and the closed loop system, right, to be non-causal. What do I give out? Like what do I essentially lose, right? So can you think about that? Or what is the trade-off?
The weightage of positive.
I'm sorry, what is it?
The weightage of the past events will get reduced and it will anticipate for the future also. Is like understanding correct?
See, the question which I am raising, okay, you can think through and come up, in the next session also, right? So let me repeat the question. That is, if we have, the overall system, okay, to be non-causal, all right? So not only the controller block, let's say the open loop transfer function and the closed loop transfer function to be improper transfer function, okay? then what happens? Okay, so yeah, my suggestion is that like please think through and then you can get back. Okay, all right.
Okay.
Yeah. Okay. Fine. All right. So yeah, any other questions? So if you look at the PID controller, so the transfer function of the PID controller will be Kp plus Ka base plus Kds. So if we simplify this, we are going to get it as Kps plus Ki plus Kds squared. So immediately you can see that even the PID block is an improper transfer function, right? Block, because it introduces two open loop zeros and one open loop pole at the origin, right? The value of the numerator polynomial, the order of the numerator polynomial is more than the order of the denominator polynomial, right? So it introduces two open loop zeros, okay, one open loop pole at the origin. Okay, so one can immediately see that as a standalone block, it's not a proper term, right? So ultimately, you can observe that the PID controller is one of the most common controllers which is used in practice, and that's why we are going to study that first. Okay, how do we design this? So immediately we can see that the ultimate task, even if we are looking at the task of determining this controller, right? I told you that typically the plant transfer function is given to us, the feedback path transfer function is given to us. So P of s and H of s are known, right? So the main task will be to design the controller. And if you use a PID controller, we have selected the structure of the controller also. So then what remains? So ultimately, we need to determine the values of this set, what is called as a controller parameter set, Kp, Ki, Kd, okay, that would achieve closed loop stability and performance. Okay, so that is the ultimate aim. Okay, so you can see that the problem we have been simplifying or like refining the problem. Let me put it that way, refining the problem to such an extent that we are essentially coming to a stage where we are saying, hey, look, the overall problem of controller design, let's think of it as a problem wherein we want to get this set of controller gains or parameters. Okay, so this is a general set of controller gains or parameters that will help us in achieving some desired performance and stability first, of course, and then desired performance of the closed loop system. Of course, is it an easy task? Once again, there are challenges. Okay, nothing comes free, right? So even if we take a proportional controller, okay, let me articulate what are the challenges. Even if we take a proportional controller, please note that we have only one parameter, right? So we need to figure out only Kp, but Kp is a real number, and so it is going to vary from minus infinity to plus infinity. So how do we choose Kp? How does one choose the value of Kp? Okay, so in an infinite set, okay, of parameters, right? So that's a challenge, right? So it's like this is a very interesting problem wherein even if we have a proportional controller, which is the simplest controller, like we have only one design parameter, which is the proportional gain, but the proportional gain itself needs to be chosen from an infinite range, right? So we need to choose one value, okay, of Kp. Suppose, let us say I have a method by which we say, like, look, choose the value of Kp between 5 and 30. I'm sure all of us will appreciate it, right? So, see, we don't need to prescribe exactly one single value of Kp, right? But however, if you essentially look at, like one, what to say, single value, sorry, one range, like by doing some analysis, of Kp, wherein we can say that, like if you choose the value of Kp in that range, the stability and performance of the closed loop system would be met. That is going to be much beneficial to us, right? So that's something which we are learning, going to learn how to do, right? Now, if we look at the general case of PID, what happens? The problem becomes even more complex, right? So the PID controller is a 3-parameter controller, right? So we'll have Kp, Ki, and Kd. So we have to visualize a 3-dimensional controller parameter space, right? Now we need to choose one point in this. So I hope the problem becomes, or the challenge in the problem becomes very clear to us, right? So this is what we call as a controller parameter space. In the case of the PID controller, the controller parameter space is 3-dimensional space, right? In the case of, let's say, even a proportional controller, like we have only one parameter, but even that problem is challenging, right? Because still, once again, we need to choose a value between minus infinity to plus infinity. Okay, there the controller parameter space is straight line, right? If I have a PI or PD controller, I am going to have a controller parameter space that is going to be a plane, right? So consequently, we can immediately observe that as we keep on, going to more and more complex controllers, the dimension of this controller parameter space keeps on increasing. And finally, when we want to implement, okay, we want only one point in the space, right? So how do we select? Suppose, let's say I ask you to select a number between minus infinity to plus infinity for a proportional controller, right? Each one of us may randomly select one number. But how are we sure that the number that we have selected will ensure closed loop system and stability? That's what we are going to learn. Okay, we are going to learn methods and tools, design tools, by which we narrow down these controller parameter space such that we can prescribe ranges or regions in the space wherein we will achieve closed loop system stability and performance. Okay, so that is what we are going to learn as we go further in our course. Okay, so I hope that is clear to you, all of you. Okay, so what is this PID controller, and what are the characteristics associated with PID controller, and what are some corresponding questions to ask? All right. Okay. So any questions based on this? Okay. So if not, I will stop our discussions for this session here, and then we will continue in the next session. Okay? Thank you.